This is Jeff and I are kind of starting our own sort of thing called the Battery Pack, discharging monthly, and each month we're going to be covering different topics. So this is our first one, and we plan it to be kind of a repeating segment, which is basically who's doing it well, bullish and bearish cases in energy storage. And this first one we're going to be doing in collaboration with Battery Brunch and probably some of the other ones in the future. What we plan to be doing with these is we're actually going to be recording when Jeff and I do these and then putting them up online as a resource for people. And then also the presentations will be online as a resource as well.
Yeah, the goal is to have this be completely transparent. Aubert and I talked a lot about this, but we didn't, part of this is we do it on our own time, and we wanted to do what was fun for us. And I think it's fun for the community too, who have a lot of questions about some of these companies and our conclusions. And then three, we just want to have fun with it. So for this is kind of our fun approach, and we figured there's a lot of people here who would love to hear about, what professionals' takes on certain companies are and why they're doing it well, and whether you can gather some insights from that or not in terms of, maybe changes you make to your own group you're working in or something like that. So just simply, we are professionals and we aim to support really conversations across different players in the field of energy storage. We want to speak the unspoken in battery science, the pain points, so to speak, that nobody wants to talk about. Something that you aren't going to see in a lab in academia, or something that if you just join a startup company, you won't see until you're, pre-production and you're running into suddenly doing hundreds of meters of web at a time. And then also we want to just share some non-confidential lessons learned, right? Nothing that's going to break the bank, but maybe something that you yourself could take and use in your own work, right? For example, where to get the right equipment, who to buy powders from, who sells small quantities, who gives you the best quality of this, where do you find specialty equipment, stuff like that. And also we want to discuss it with a critical eye and do a bit of critical thinking on why we made some of these conclusions.
So those of you that have seen our previous talks, we'll just give really quick summaries, but one of them was Surviving the Valley of Death, and you see on the right this sort of roadmap from R&D through commercialization to actually success as a business. It's an enormous amount of money and a very long amount of time. And so the basic lessons, stay focused, stay in touch with your markets, talk to customers early, make sure you actually have a customer if you hit certain technical specs that you're working towards, stay lean, target high value, low quantity applications to start so you can actually meet the demands of the markets you're aiming for. And kind of one of the big lessons I always try to hammer down, because I've worked with so many different startups in different spaces, is success for the company does not necessarily mean success for the founders, executives, or the investors. And vice versa, right? And so you can have a success story being a small company into a small high-end market. It's not going to get you on New York Times news the way that Solid Power QuantumScape SPACs will, but you as an investor or as an early founder, co-starter would probably have a better success story out of that.
And we'll bring up a company that's a good example of this that goes really under the radar, but we're very bullish on in terms of what we think their tech's application can do and how it can really help the industry.
Yeah, and all of these previous talks, the presentations and the notes are available at the Battery Brunch notes, and this will be put up there as well after this. Mm-hmm. You want to tackle this one, Jeff?
So, the second talk we actually carried out was this whole talk about engineering into the box or not. And it was really a discussion around, one, how do you leverage existing technologies to accelerate your special technology, whether that be a material, whether that be a component change, whether that be like electrolyte, or maybe some way you form the battery. But how do you change the attitude of people who are trying to really come into this space and make everything brand new, and get them to think, okay, that's really cool that you can do that, but you need to be able to plug this into a multi-billion-dollar manufacturing facility. And if you can't do that, then do you even have something to start with? And that brought about the idea, how do you engineer into that box yet still be creative? The second one is, no, you can keep going.
Okay.
Or the third one, I guess. Is what we did a talk on pain points, and this was a great talk where we went over the little things. How do you slit lithium correctly without gunking up your machine was an example of this. Or who do you buy electrolytes from? in quantities that aren't going to kill your pocketbook, but you'll be exactly certain that you'll have a good quality electrolyte? Or who gives you the materials, or who do you buy equipment from if you want to go, how do we avoid MTI? What can we do to avoid MTI, right? Um, and like that brings the whole thing. It's like, oh no, when did this become a problem, right? Because we want to have that discussion where a lot of startups come in and they think they're doing really great in their coin cell data, and then immediately they need to make multi-stack pouches, and it's like, oh, when did current share become a problem? And nobody thought about binder migration inside the slurry as it dried, and uneven coatings, and how that affects your performance. Um, and then we've summed it up with the fact that, like, in reality, the last 10% of your hike is going to be 90% of the work. It's perfectly uphill because suddenly you have QC to do, scale to do, and performance all at the same time.
And you're on a time crunch and your money's running out.
Exactly. Aubert, you want to do this one?
Sure. So the last one we did, which was the last battery brunch, was basically matching your technology to your actual market and sort of debunking the silver bullet concept in batteries, where really what that comes from is people trying to raise money have to say that their battery can hit every market, every application, is going to have the biggest, widest market share possible in order to get investment. And really that's not true, because any time you push one aspect of a battery, there's a give somewhere else in the spider diagram. And I resisted putting spider diagrams in here, but the point that we used was the battery that's going to go on a soldier for sort of warfare communications is not the same battery that's going to go into a Tesla. They have, we covered last time, like very different performance requirements, different cost requirements, different material requirements, different priorities, and pretty vast trade-offs that were made in choices between those two categories. And pretty much every different major market has their own version of these trade-offs. A lot of times it's even something just as simple as, they can take less performance because they need less cost is a really big one. So, this is, how do you stay kind of focused as a company? What's the best, technology and form factor for your chemistry? Where do you aim? Understanding the real performance needs of your application. What's the highest priority, second priority, third priority, and what ones can you maybe give to get to there? And then, testing. Testing really matters, and how, real life usage profiles really matter. And you don't have to sell to everyone. If you're making something unique, you can certainly find someone that needs a unique technology that you can fit it, that you can provide. And so you just have to find that market.
Yeah, and like just to jump onto that one real quick, like remember everyone, like the whole point of this talk, and Aubert went over it perfectly, but like the whole point is like there is a technology for solid state, or an application for solid state. There is an application for silicon. There is an application for lithium metal, thin film lithium metal, thin film cathodes, large pillow-sized pouch cells like you see at Solid Power, and everything in the above. And it's just a matter of you finding it and actually applying to it, right? For example, I will give you a great real world. If your battery cannot go more than 250 cycles at full DOD, that's okay. The DOE wants, or the Department of Defense wants to talk to you, because that is what some actuary figured out inside their offices. That was the max battery life that they had to deal with. And if you could give them more life or more length on or time on the battery at a cheaper cost, they'll talk to you with only 250 cycles being the threshold, right? And those are pretty low. Even drone batteries are 140 cycles full DOD. So those are great examples of not having to hit did it go 6,000 cycles because we want to drive it for 50 years, right? So those are great examples of.
Thank you, Derek, for posting some spider diagrams. You get points from me. Thank you. Right. So let's get to the sort of meat and potatoes. So today, sort of what we basically did is we've picked a number of companies that we think are doing it right. We figure we're going to be positive and complementary. Our first one of these, and maybe save our negative comments for a future one of these presentations. So we're going to be covering Solid Power, Cuberg, and Northvolt. There's some synergy there, as many of you know. And the last one is Soteria, which is a material company, which I hope some of you are familiar with. And if not, we hope to tell you a little bit about them. And basically, we're going to be going over sort of what their product are, sort of their specifications, what makes them special, kind of what their basic pitch for the company is, and then kind of grading them on these things we've already discussed, right? Sort of what are their unique strengths? What are their pain points? Are they engineering into the box or not? What have they done or what are they doing to survive the valley of death? And I'm forgetting the last one, Jeff.
The application. Are they
Oh,
targeting the right
and
application?
are they correctly targeting their technology to an application?
And then we got a fifth one, which is super qualitative. It's the qualitative metric, whether we like them or not. And this is also where I want to caveat this entire talk with like, Aubert and I are battery professionals, but this is our opinion. This isn't like some factual knowledge where Aubert and I are, shaking hands with all the engineers inside said company and giving you all the dirty details. We know a lot, but no more than I think the really determined researcher couldn't find out. And we're just giving you our perspective, right? So we want to catch it all in that because we don't want to, lead people in the wrong direction. This is something where this is our viewpoint, and as such, we'll try to keep it very factual based on observations from the outside, and we'll go forward with that.
And when it's simply a qualitative, like we like them, we'll try to give you the reasons why too.
Yeah.
Okay. So first company we're going to go over is Northvolt.
And Northvolt's an interesting one, actually. I think they're like, quite frankly, and I think Aubert and I agree on this, is they're doing something interesting because they've taken what we think is a really unique approach to the battery space and manufacturing as a whole. And from that standpoint, right, if we look at how batteries are made, if we look at what everybody's been doing from Panasonic to Samsung to LG to CATL to Tesla, working with Panasonic to other people, there's usually three primary plays that you're seeing a lot of in industry. One, the most obvious, is they're trying to get cheaper, higher energy density materials, right? Examples of that could be silicon, examples of that could be sulfur, examples of that could be just going to pure lithium metal, right? Going to lithium iron phosphate would be another example of changing up the cathode. The second play that you usually see is a very strong push towards vertical integration, right? Companies are starting to buy up and down the supply chain such that they can take out transportation time, they can take out cost associated with getting cert marked up by every step of the way. And then the final one that you see a lot of is just, oh gosh, it escapes me a little, but changing form factors of the cell, changing cell designs, right? So an example of that is getting rid of your electrolyte by going solid state. Instead of making a 21700, we make 4680s. Instead of pouch cells, we go to large, super large prismatics, and by scale, you reduce the cost that way. Northvolt's really interesting though, because Northvolt's approaching it from the energy that they pay to get the factory running. And if you think about that from the standpoint of if you're producing 35 gigawatt hours a year of batteries, right, you need to have, you have to charge them when you form them. And that is a lot of electricity every year that you have to pay. And Northvolt's going with the approach of using clean, renewable energies that are cheap as a way to power all their factories. And that's, and to me at least, and Aubert can pitch in here, is actually something I find really cool about Northvolt. Now I do have my reservations, but I think from just an immediate look from the outside in, they've taken a really novel approach. They're not trying to break the box with going way too far outside. They've talked to the right people, and they have a lot of backing from VW and a lot of European businesses. And they're putting themselves in a spot where they're, where companies or countries are starting to get more and more nationalistic and worry about supply chain issues out of China. They're positioning themselves to be like, hey, we can do this for you and alleviate a lot of those concerns in the government.
Yeah, and just to touch on that, they seem to have made really good strides in sort of securing their supply chain and their end markets already. And so really what the only reason their score is not higher yet, and we'll get to some of their new novel technologies in the next segment, but basically one of the reasons they're not higher is sort of really the question of kind of what differentiates a tier 1 from a tier 2 from a tier 3 manufacturer. And they haven't really proven yet until they've actually built these plants and actually shipped the cells that they can be a tier 1, but it looks like they might at least in the way they're positioning themselves from location, from energy cost, from supply chain setup, and from their sort of pre-set up markets they can sell into. It looks like they're setting themselves up to actually be a tier one if they can pull this off. And so that's kind of where we came to this conclusion.
I mean, the flip side of that, right? Just after waxing poetically about everything I like about them, I do have a lot of questions. One, they're entering into a game where you have tier ones making a constant 8% to 3% improvement every year on energy density, and if you're entering with the pre-existing tech without any kind of advantage in terms of you figured out how to increase the energy density, you figured out how to, you know, make cells cycle longer, deal with less thermal issues, right? You're already behind the eight ball, right? Just getting to the same place they were the year before doesn't make you a tier one, right? What makes you a tier one is you're competitive in one of a few categories in terms of all around cell performance. And then on top of that, right, they're going to run the same issue Tesla is. Why isn't Tesla mass manufacturing batteries for all of their cars and all these other applications if they're so well and vertically integrated? And the answer really to that question is the QC and performance scale up, right? Elon Musk himself has said the hardest thing he's ever had to deal with in a business is manufacturing at scale. And he comes from, if I remember correctly, he comes from PayPal, where manufacturing at scale is a very different concept than it is in the auto industry, where Teslas are notorious for having QC issues. And in the world of batteries, unfortunately, you can't bin, or you can't go back to your battery and tweak the thing that was slightly out of spec. You lose that entire lot, and that's a huge amount of loss, because you've put essentially 3 weeks of effort into making these batteries, and all it took was your separator was slightly out of spec, and now it's slightly too thin for the current rates, and now it has overheating issues, and it might shrink and cause a huge short and a big fire. And all it takes is like one of these batteries in a car to have a small slight QC issue for a huge recall. And that's not something that doesn't talk about, and that's what Northvolt's going to have to face, right? If Northvolt supplies Volkswagens with millions of batteries to put in all their cars, and one of those batteries has a QC issue, Volkswagen has to recall all those vehicles and replace the batteries if they can't fix it magically somehow externally. And if you think about that over a 3-year span and the amount of vehicles they sell, the question would be, could Northvolt survive the financial impact of replacing all of those batteries? So did they survive that death? Honestly, that's a we'll see. Right? They have to perform at scale. They have to show they have good QC, and they have to show they have a low failure rate. Are they in the box? Oh yeah, 100%. And as far as pain points go, I give them half a point there. They're going into a well-established area where equipment exists to do exactly what they want to do. They aren't having to reinvent any wheels. They aren't having to reinvent new technologies. They're just having to get their formulations correct. And as far as realistic tech for their claimed application, they're 100% spot on. They went and they partnered, like Aubert said, with the right people. So qualitatively, right, in our qualitative approach, we like them, especially since what they did to shore up their weaknesses on coming in with not only the same technology, but giving themselves an avenue towards the new technology, which is a good bounce to our next topic.
So our next one is Cuberg, which, as everyone knows, was basically acquired by Northvolt. So, I think it's to start. I just kind of want to go back, and I've sort of been aware of Cuberg since I first started at Spectra Power. And full disclosure, they were a customer to Spectra Power before I joined, but the founders basically stayed really lean. They kept the company very small. They stayed extremely focused, and you can look at some of their older sort of pitch packs that they did, and it's very impressive how little money they spent before they kind of got traction, and then they just stayed really focused and ended up aiming towards their basically special electrolyte for commercialization, and they got picked up. And so from a company perspective, I think the company was successful in the acquisition, and what remains to be seen is whether that acquisition by Northvolt enables them to kind of go through the other side of manufacturing to sort of commercial success.
Yeah, and I mean, we can honestly just check off survive the valley of death, right? You got acquired. Buy another startup, but you got acquired. So clearly you did something well, so they survived that. Their
I feel
engineering.
like I feel like billion-dollar companies aren't allowed to be called startups anymore. I think.
Do we need like a threshold for startups? Throw it
Yeah.
in chat. What do you think the startup threshold is? What
But you
valuation?
still have a valley of death ahead of you in a
Oh,
billion
of
dollar
course.
company. Don't
Yeah.
kid yourself.
Oh, no, no,
You
no,
know.
no. For that, yes. I just think they don't get to be called a startup when they have that much money. That your point completely taken. I absolutely agree with you. No, no. Every company, regardless of size, if you're going into manufacturing,
Look at Lord John Motors. Okay,
yep.
they had a billion plus, and they say they can't produce their product, and they're looking at some real problems. So it's very easy. See, when I look at this, and I've done a number of these things, every one of these things, you're absolutely right on your page about what to do.
Mm-hmm.
But and it's real easy once you think you've done that to forget that still is
Oh
there
yeah.
again and again and again.
Yep.
There's
So
a huge issue, right, when you talk about manufacturing at scale, which a lot of people don't realize, right? We can all make a liter of electrolyte. It's a different thing to fill up a swimming pool with electrolyte and have that swimming pool be the exact same thing you take every aliquot from, right?
Yeah.
What is the shelf life of that big of quantity? How long does it last? Does it ever fall out of solution over an X period of time frame? Shelf life is huge. But as far as in our eyes, right, and I'm going to push this, that I think they survived the Valley of Death. And I'm not saying that they survived in the sense that they have survived and made it to scale and everything. I think they've survived in the sense is my guess is their original company goal was to produce something useful to someone else who someone else finds useful and get acquired. Um, and to that end, I think they succeeded. Um, as far as engineering into the box, I think they are because they stayed in a liquid-based system, and as long as you're staying in the liquid-based electrolyte system, you do run into less hurdles. Your hurdles, though, right, are going to be really associated with what you're putting into it. So as far as pain points, I took points off there, right? So if you look at it, they do sell a lot about their lithium metal compatible liquid electrolyte. They do sell a lot about how it's really safe. If you look at a lot of their old pitch decks, if you look at a lot of their old newsletters, they have figured out how to have a liquid electrolyte that gives you the same rate capabilities that you see in current modern day batteries, but you gain a lot more energy density with it, and it's a lot safer with pure lithium metal. And when I saw that, I went back, I did some patent trolling, I did a lot of research, but generally speaking, when I ever hear someone says they have a safe liquid electrolyte, there's really two obvious options. One, their water-based, aqueous-based system. And last time I checked, they're working with lithium metal, so we know they're not an aqueous-based system, or else they would just not have a functioning battery. Two, they're relying heavily on ionic liquids, right? Like for example, like pyridinium, LiTF, pyridinium 1,3 or 1,1 or 1,2 FSI or something like that, because ionic liquids tend to add a lot of safety and stability to the electrolyte system, tend to also not immediately combust on you, so you have a lot of lead time before you have any big negative disasters or events, and they tend to bring a lot of stability, but they are not actually really greatly known for stabilizing the lithium metal anode. They're really good for like just making the electrolyte safer and being a way to add improved mass transport. So that then led to the other thing, which I know is really hot actually in the lithium metal world for bespoke electrolytes against lithium metal cells. You'll see it a lot in the NMC. They've switched over to LiFSI, LiTFSI as their primary salt because it's fluorinated, which is good. It has really good conductivity, but what it really does well is it's very compatible and stable in fluorinated ether electrolytes. And that's what we're talking about in terms of like TTE, HFE, MTBE, DIPE. There's a long list of these fluorinated ether electrolytes, but if you look at the approach, and the big push actually even from a government side, everybody's going towards heavily fluorinated ether electrolytes. And then on top of that, they're coupling it with like a good surface modifier. So DME or dimethyethioxane is a great example of a ether-based solvent, has a lot of compatibility with the lithium metal surface, and if you couple that with something that you are going to decompose into a heavily fluorinated lithium compound like LiF3 or something of that nature, you combine those two with LiTFSI, and you can actually push a lot of stability. I'd like to point out actually that if you follow traditional battery manufacturing practices with a carbonate electrolyte right now, and you don't go, cycling your cell at C over 1C and you do like C over 5, you can get 50 cycles out of lithium metal, right? So if you think about it, 20 micron thin lithium layer, as long as you keep tweaking the electrolyte to provide some sort of surface compatibility, you should be able to actually stabilize the cell. But the last, kind of thing on that is usually these electrolytes with TFSI and DME and heavily fluorinated against a lithium metal anode with some sort of ionic liquid, they tend to not be the most under rate. They do not do the best of things. They are very aggressive towards lithium metal under rate, to the point where the moment you back off rate, you're going to see huge losses in terms of your coulombic efficiency. So if you were straight cycling a battery at 1C for 100 plus cycles, it would look fantastic. But then the moment you back off to C over 5, you would see a 10% drop in efficiency as it tries to repair that layer, because the fluorinated electrolyte at that point is just going to be a consumable.
The other big thing, of course, is that all of those things add a lot of extra cost. And there's also a lot of extra complexity in the ionic liquids, and there really isn't a supply chain built for them. So one of the kind of pain points that both Northvolt and Cuberg by proxy are going to have to overcome really is being able to create or organize the supply chain for those things, both from a quantity perspective, a quality perspective, and a cost perspective. Now, to be fair, what it allows is in the spider diagram, it allows you to push out the cost to increase performance in several categories, right? It should make it safer. It should make it higher energy density, so as long as your sort of the whole package of what you're aiming towards the market works with that, it looks like that piece of it would be successful, and just kind of remains to be seen what they can do at cost. So at this point, I think we've covered our first 2 of the 4, and I didn't see the name of the gentleman that talked earlier, but thank you for jumping in. But now we're actually going to formally open it up to the Q&A session for the first 2, and then once we finish that, we'll start the next company review. Oh, come on, this group always has questions.
Yeah, come on, guys.
or at least comments.
You guys always got something. There's 40 of you. Come on. Nobody has a question. We were that covered that well.
I'll shoot. So what are you thinking about in terms of application here with the lithium metal cell with the liquid electrolyte?
Honestly, lithium metal is going to be a really great application for stuff with medium cycle life requirements. So DoD, lithium metal is going to be good because, one, you're not talking high rates, right? If you look at military communications, right, low power usage just needs to last a very long time, so the relative current rate is relatively slow. If you look at drones as another great example, lithium thankfully has no real mass transport problems, right? You can plate lithium as fast as you want. So if you think about it from that standpoint, missiles or single flight, stuff like that, where you need high capacity and high rate, more so than a primary, it's going to have a lot of push there. So I think missiles, if I remember correctly, are 25C is the current rate that you have to be able to hit. So you're going to plate no matter what. The other stuff I can see a lot of it in is stuff like your cell phone, right? Unfortunately, guys, I wish our cell phone batteries lasted a lot longer than they do, but there's something called planned obsolescence in the industry, and the reality is they don't want your phone to go more than 200-ish cycles, because at some point you have to buy the iPhone 52 with the big screen and the plastic casing. That's just what Apple wants from you, and you've bought into their ecosystem. And I can't say I'm any better because I own an Android and Google owns my soul as well. So, the reality is, right, those medium cycle life applications are great. If you look at stuff like medical, you're not going to have a lithium metal battery, right? That where safety is paramount, even if you say it is safer than the comparison, right? Life suddenly adds an extra layer of hurdles that you have to actually overcome. And that's why in a lot of like soldier applications, right, it's cool if it's on like the comm equipment, but it's not cool if it's like what's powering like the dude's night vision or stuff like that, right, where like it is necessary to their mission or it's imperative and that it could really affect their life. So that's like the application space.
You think there's any pathway to get this into an electric vehicle?
So if there's a lot of scale-up issues. So but basically, aside from all the issues of the lithium metal piece of it, just the ionic liquid piece of it, right now there's basically no supplier. And it's typically they're very expensive. And so in order to get a lithium metal scale in production with these ionic liquids, they have to scale up the ionic liquids. And that's the entire supply chain kind of needs to be set up for that.
And then, like, if you think about it, I brought this up earlier, how do you slit a lithium metal electrode? Right? Like, you have this very soft, ductile metal that wants to stick to everything. You aren't going to laser slit it because you're going to just recrystallize whatever's on the edges, and we don't know what you're adding when you do that, even in a dry room. You aren't going to do this in slitting in a perfectly clean argon environment. That's not really scalable. I'm sure there's someone who could figure it out and build this entire fancy line and run argon gas or something, and you're kind of limited to argon because if you put nitrogen in it, you'll have the nitrogen react with the lithium. So slitting is even just like a simple manufacturing problem nobody has talked about. Right?
One basic thing, one way to look at, right, is pretty much any change you make to a battery, you change one thing, kind of other things change too. So really what this is they're adding safety and compatibility with lithium metal. That adds more energy density, right? And what they're giving up is really fundamentally, they're giving up higher cost. It's going to be a much more expensive battery.
Yeah.
Now, as something we've talked about before in other talks, like there's a huge difference between a commodity product where when the cost goes up, people don't buy it, and an enabling product where if you don't have the performance metrics in the enabling product, your application doesn't work. And so from things, everything from short-term CubeSats, military applications, drones, other things that need the higher energy density of lithium metal but need to be safer, but they don't care as much about cost, there could be a play here for these batteries to work.
The government pays $80,000 a kilowatt hour, guys. So, the room for cost absorption is high.
Oh, sorry.
We have 6 minutes. Other people want to hear about the other topics, Aubert. Let's
okay,
go.
all right. Okay, so we're going to go to the next one. So here, I just clicked it. So the next one we were going to talk about was solid power. Sorry, you guys had to choose. It looks like also Hui from Amsera was discussing solid power and QuantumScape today. But I can't see what we wrote.
Here, I got it. Okay. So solid power's got two really main tracks. They have a high content silicon anode they're working on, but they also have a lithium metal anode. Really, solid power's primary play here is safety, and they're doing this safety and energy density, and they're really doing this through sulfide-based solid electrolytes. The reason they're choosing sulfide over oxide is primarily focused on the fact that sulfides are great ionic conductors. So as we all know, usually the big dig at solid state is, well, like, cool, you perform, but you're heating your battery to ADC, right? So that's the big driving force for all of these solid state battery companies is how do we get reasonable performance at room temperature, right?
And low pressure.
One thing I do, and here's the thing, I like Solid Power actually as a company because they make pouch cells. They make big pouch cells. They've shown they can make big pouch cells. They're constantly making big form factor cells. Now, will this ever go into a cylindrical cell? Not in the near future. No way. There's a lot of R&D that has to go into that form factor, but the fact that they're making multi-stack pouches is great to me. One thing I really didn't like when I was going over their investor deck was this charge in less than 20 minutes for a lithium metal anode in solid state. And that is just, if you look at the data they've released and you look at the data that they're claiming in their pitch decks, right? Like this feels very what I would call like the PowerPoint spec, right? Where they were cherry picking different cell chemistries and what they could do and then adding it together to make it seem like it's one cell chemistry that does all these things, where it could have totally been like, instead of the 150 micron thick NMC cathode, right, they're running a 20 micron thick NMC cathode against lithium metal with like a 2 micron solid state layer, and that's how they're getting 20-minute recharge times, right? So, and then the cost is also the other one I'm very cautious on when it comes to sulfide-based systems, guys. Sulfides are super reactive. Like we're talking like pretty next level reactive. Like almost, I would actually say lithium sulfide is probably more, in my opinion, reactive than lithium metal in a dry room. I'm caveating this in a dry room. Lithium metal is very reactive, but in a dry room, I would say, because the problem with lithium sulfide is it's very, 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 very reactive to water, and it is very easy to start putting like a native oxide layer on the surface of it. So it's hard. I like them a lot, but at the same time, like they're currently going to deal with the whole thing where they're saying, you know, they're producing 100 kgs a month, but we don't know what the quality of that 100 kgs a month is, right? You could produce 100 kgs of like medium grade material, but like all your battery performance is on like ultra high quality grade material. So there's a lot of like missing check boxes that I didn't see when I went through their company and did research on their product. But overall, I think they have the right mentality in that like everything they're demoing in full cells. Like I know Aubert got some cells from Solid Power when they were at a trade show and they were handing them out, and I think that's like pretty.
And that was that was 4 years ago, guys. That was in like 2017.
Yeah, so like they're pretty gutsy. So like we give them a 3 out of 5 because really the problem is I don't think they survive the ballot. It's this valley of death. I think they're doing good with engineering. They're going into the box. They're making full cell pouch cells. This is fantastic. Pain points, I don't think they've done it. And as far as realistic tech, they're going towards EVs. And I still find it hard with the consumer demand, right? Everybody wants fast charging. I find it hard for them to hit EVs with solid state right now, unless there's some paradigm or breakthrough in the technology. Let's go to the next one, though, just so we can clean up, and then we can always go back.
Okay, so we'll do questions at the end then. Okay, so this one's a little bit of a detour from the last couple ones we talked about. We basically have sort of two. You know, we've got an electrolyte for cell company, we've got a manufacturing company, and the last one was Solid Power, which is sort of a bit of each. So if you're not familiar with Soteria, Soteria has some very novel battery safety materials, and kind of their core concept is. If you look at sort of the middle bottom of the page, on the left side is sort of a standard lithium ion cell architecture, aluminum and copper metal foil current collectors, and a standard, you know, plastic ceramic coated separator in the middle. When you get a dendrite or metal defect or burr or anything else, you know, a nail going through the cell, what ends up happening is the plastic separator heats up at lower temperatures and will pull away from the short, and then that lets the short get bigger and worse, and then all the current goes in and you get our traditional battery fires, right? Which is why lithium ion tends to be so unsafe. Their architecture kind of changes the three components there, where they have these aluminum and copper coated current collectors that are made of like polyamide plastic materials. And so what happens when there's a short, almost instantaneously, it acts like a fuse and it just pulls away from the short. And the difference with their separator is they use a sort of like aramid Kevlar fiber high temperature separator. And what that does is it doesn't pull away from heat. And so what you end up getting, and I highly recommend people go look at their website if you haven't. They've got some really cool cell thermal runaway nail penetration testing, and actually some really cool ones that were done by Eric Darcy at NASA, where you can actually see their cells with nails going through them being CT scanned, and you can watch what happens to the components in theirs versus in traditional cells.
And the last 30 seconds, guys, the reason we like them a lot, this is a cool play. They aren't trying to change and run into chemistry issues where it's like, oh, we're going to use like silicon, solid state, sulfide, lithium, sulfur, et cetera, et cetera. They're coming in being like, we're just going to take out 20% of the weight of the battery using this cool trick. And it's going to add some safety, and that's all we're doing. And they're getting people to do the work for them, which is like the most baller thing you can think of.
Nice.